Swayam Prabha. Digital India. Educated India.
Welcome to lecture 12 of the course on time series modeling and forecasting. In this lecture, we will consider different stationary processes for modeling a time series. In particular, we are going to consider the moving average process in this lecture. Now, these stationary processes which we are going to discuss help you in modeling how the time series has evolved. Means you assume that your time series has evolved from the past observations and past shocks. So, how your time series has evolved through past shocks and past observations, that is the basic purpose of studying all these stationary processes. Okay. So, suppose you are at a particular time point t. So, up to time point t, you have t minus 1 past observations, y 1, y 2, y t minus 1, and then you have t minus 1 random shocks up to time t minus 1, u 1, u 2, u t minus 1. Then at time t, you have a random shock u t. Now, there are three possibilities. There are three possibilities for the evolution of y t. First possibility is the process has memory of random noise component of where it was, means the random noise corresponding to past values of y. So, y t has memory of past values of shocks or past noise corresponding to past values of y 1, y 2, y t minus 1. Now, the shock corresponding to y 1 is u 1. The shock corresponding to y 2 is u 2, and so on. The shock corresponding to y t minus 1 is u t minus 1. So, y t has memory of y u 1, u 2, u t minus 1, but it has no memory of where y was. It does not have any memory of y 1, y 2, y t minus 1. Then the second possibility is that the process has memory of where it was, means past values of y. So, in the evolution of y at time t, y t, y 1, y 2, y t minus 1 have played direct role, but u 1, u 2, u t minus do not have any role. So, the process has no memory of random noise corresponding to past values of y. This is the second possibility. Of course, the role of ut will always be there, because ut is the shock corresponding to the present time series observation yt. So, it is always going to play a role in determining the value of yt. So, in the first case, actually these are the random shocks u1, u2, ut minus 1, which are going to play a crucial role in determining the value of yt along with ut also, but y1, y2, yt minus 1 do not have any role, do not have at least any direct role in the evolution of yt. In the second case, these are the past observations y1, y2, so on yt minus 1, which have direct role in determining the value of yt. Plus ut is also playing role, the present shock, but the shocks corresponding to the past time series observations do not have any role to play. Means u1, u2, so on ut minus 1 do not have any role to play in determining the value of yt. Then naturally, there is third possibility also. The process has memory of where it was, means whenever we say where it means past values of y, and it also has memory of random noise corresponding to past values of y. So, the process has memory of both the past values of y as well as the past values of random noise component u1, u2, ut minus 1. Again, ut will always be there. So, these are the three possibilities, and these three possibilities are the basis of defining three processes. The first one is the basis for moving average processes, the second one is the basis for autoregressive processes, and the third one is the basis for defining mixed autoregressive moving average processes. Now, in the first case, the value of yt is determined by the past shocks or the shocks corresponding to the past observations. So, you may write yt as a function of u1, u2, ut minus 1, and then ut will always be there. In the second case, these are the past values of y, means y1, y2, yt minus 1, which are going to determine the value of yt. So, yt depends upon so, you may write yt as a function of y1, y2, yt minus 1, and then ut will always be there. And in the third case, both the past observations and corresponding past shocks are playing role in determining the value of yt. So, yt is actually a function of you can say G double star y 1 y t minus 1 as well as u 1 u 2 u t minus 1, and then you add the present shock say. So, these are the three possibilities. Now, first we consider the first possibility, and so we define the moving average process. A process y t is called a moving average process of order q, where when y t is equal to mu plus u t plus theta 1 u t minus 1 plus theta 2 u t minus 2 plus 1 plus theta q u t minus q. So, basically apart from u t, it is the linear combination of shocks, past shocks, which are determining the value of y t, and past shocks up to what extent? Past shocks up to lag q u t minus q. Then we scale u t so that the coefficient of u t, say theta naught, is always 1. Means if the coefficient of u t is theta naught, then you can always write it as say v t. V t is also a purely random process. So, you can always adjust u t so that the coefficient of u t becomes 1. Then theta 1, theta 2, so on theta q are the constants which may be positive or negative. So, these constants are actually assigning the weights to past shocks, how much role these past shocks are going to play, or how much role each of these past shocks is going to play. The weightage of u t minus 1 is theta 1, weightage of u t minus 2 is theta 2, and so on. And the model has q plus 2 parameters. Q parameters theta 1, theta 2, theta q. Then you have mu and sigma square u. Sigma square u is the variance of u t. So, basically MAQ process represents y t against current and previous error shocks u t, and a constant mu. This is also called long term mean. It remains there for all values of t, it does not diminish. You can write the process in this form: y t minus mu equal to summation j equal to 0 to q theta j u t minus j. Again we are writing theta naught equal to 1. Now, this is actually a moving average of white noise u t, or these past shocks. That is why this process is called a moving average process. Again, the process does not have memory of exactly where it was, means past values of y. It does have memory of random noise component of where it was, means noise corresponding to past values of y. The value of y t is determined by the random noise corresponding to past values of y, not by the y's past values of y directly. So, this is the MAQ process, and then we obtain the mean of the process. So, expectation of y t, you know that expectation of each of these components u t minus j is equal to 0. So, the expectation of this entire second term is 0. So, expectation of y t is equal to mu. Mu is the mean of the process. Now, we obtain the variance of the process, which is expectation of y t minus mu square. So, actually sigma square y is equal to expectation of theta naught u t plus theta 1 u t minus 1 plus theta q u t minus q multiplied by square of this. And then this is equal to, now if you take a square of this, then you will get square terms like expectation of summation j equal to 0 to q theta j square u t minus j square, plus you have cross product terms. So, you have cross products also. And these cross product terms involve terms like say u t minus 1, u t minus 2 and so on. Means terms like u t dash t not equal to t dash, and for t not equal to t dash expectation of u t dash is equal to 0. So, expectation of cross product terms is 0 and expectation of each of these terms, expectation of u t minus j square is sigma square u. So, finally, you get this expression for the variance of y. Now, for q equal to 1, we get MA1 process, which is y t equal to mu plus u t plus theta 1 u t minus 1. I have also plotted a random sample of size 500 generated from the MA1 process with mu equal to 0.05, theta 1 equal to 0.7. So, this is the plot. Then the variance of the process is sigma square y equal to gamma naught equal to, now here you have just one term theta 1. So, 1 plus theta 1 square. For obtaining the auto covariance function, we have gamma 1 equal to expectation of u t plus theta 1 u t minus 1 plus into u t minus 1 plus theta 1 u t minus 2. Now, if you take product of u t and u t minus 1, the expectation will be 0, product of u t and u t minus 2 also has expectation 0. If you take product of these two terms theta 1 u t minus 1 and u t minus 1, then you get theta 1 expectation of u t minus 1 square, and expectation of u t minus 1 square is sigma square u, and then the expectation of theta 1 u t minus 1 into theta 1 u t minus 2 is also 0. So, finally, you obtain gamma 1 equal to theta 1 sigma square u. Similarly, gamma 2 is equal to expectation of u t plus theta 1 u t minus 1 into u t minus 2 plus theta 1 u t minus 3. Now, after multiplying these two terms, you do not get any term which has non-zero expectation. So, expectation of this product is 0. So, gamma 2 is 0. In fact, gamma k is equal to 0 for all k greater than 1. And obviously, gamma minus k is equal to gamma k for all k. Then you can easily obtain the autocorrelation function of MA1 process. Rho k is equal to gamma k upon gamma 0. So, we divide gamma k by gamma 0, then finally, you obtain if you divide gamma 1 by gamma 0, then you get rho 1 for k equal to 1. It is equal to theta 1 upon 1 plus theta 1 square. And all other autocorrelations are equal to 0. For k greater than 1, rho k is 0. Then just look at these two graphs of autocorrelation functions of MA1 process, and we have taken theta 1 equal to 0.7 in the first plot and theta 1 equal to minus 0.7 in the second plot, means this is for theta 1 equal to minus 0.7 and this is for theta 1 equal to 0.7. So, if theta 1 is positive, then rho 1 is positive. So, obviously, rho 0 is 1, rho 1 is here, and then all other autocorrelations are equal to 0. And when theta 1 is negative, then rho 1 is negative here, and all other autocorrelations are equal to 0. So, in fact, if you look at autocorrelation function plot, and if you find that the first autocorrelation is non-zero and all other autocorrelations are equal to 0, then you can say that this plot is corresponding to MA1 process. Now, we consider MA2 process. For q equal to 2, you have the process y t equal to mu plus u t plus theta 1 u t minus 1 plus theta 2 u t minus 2. Then variance of the process can be easily obtained as sigma square y equal to sigma square u into 1 plus theta 1 square plus theta 2 square. Then we obtain the value of gamma 1. Gamma 1 is equal to expectation of y t minus mu, means u t plus theta 1 u t minus 1 plus theta 2 u t minus 2, and you have to multiply it by y t minus 1 minus mu, means u t minus 1 plus theta 1 u t minus 2 plus theta 2 u t minus 3. Now, we multiply these two terms and we only consider those terms which have terms involving squares of u t or u t minus 1 or u t minus 2. All other cross product terms will have expectation 0. So, you multiply theta 1 u t minus 1 by u t minus 1 and take expectation. So, you get sigma square u theta 1 and then you multiply theta 2 u t minus 2 by theta 1 u t minus 2 and take expectation. So, you get theta 1 theta 2 sigma square u we are taking common and then this is equal to sigma square u, you take theta 1 common 1 plus theta 2, right. Similarly, you can obtain gamma 2 also. In gamma 2, you have u t plus theta 1 u t minus 1 plus theta 2 u t minus 2 multiplied by u t minus 2 plus theta 1 u t minus 3 plus theta 2 u t minus 4. If you multiply these two terms, then the only term which has non-zero expectation is theta 2 u t minus 2 multiplied by u t minus 2. So, you have theta 2 sigma square u. And for k greater than or equal to 3, gamma k is equal to 0. So, if you take k equal to 3, then you will have u t minus 3 here, u t minus 4 here and u t minus 5 here. So, you do not get any term which has non-zero expectation. Then you can easily obtain the autocorrelation function, just you take gamma k in the numerator and divide it by gamma 0. So, you get these expressions for the autocorrelation function. For MAQ process, obviously sigma square y is equal to gamma 0, which is expectation of summation j equal to 0 to q theta j u t minus j whole square, which is summation j equal to 0 to q theta j square. Of course, sigma square u is also here. And then we can also obtain the autocovariance function of MAQ process as gamma k equal to expectation of u t plus theta 1 u t minus 1 plus 1 plus theta q u t minus q multiplied by u t plus k plus theta 1 u t plus k minus 1 plus 1 plus theta q u t plus k minus q. Now, when you multiply these two terms, you have to collect those terms which involve a square of u's. Say suppose you take u t, then you have to find a term which involves u t here. Which term involves u t? Theta k u t plus k minus k. here. So, you multiply this u t by theta k u t, and expectation of u t square is sigma square u, and you get this term theta k sigma square u. Second term theta 1 u t minus 1, theta 1 u t minus 1. Then you have to find a term in this expression which has u t minus 1, theta k plus 1 u t plus k minus k plus 1. So, you get, if you take expectation, then you obtain theta 1 theta k plus 1 sigma square u, and so on. The last term you will get involving a square of u t's is corresponding to this term u t plus k minus q, and here with u t plus k minus q you will have theta q minus k u t plus k minus q, a term like this. You take product of this term with the last term here, then you get theta q minus k theta q, then u t plus k minus q square, and then expectation of this quantity is sigma square u. So, you get this term, or in the summation form you can write this entire term equal to sigma square u summation j equal to 0 to q minus k theta j theta k plus j, k equal to 1 to so on q, and for k greater than q gamma k is equal to 0, and of course, gamma minus k is equal to gamma k. Then the autocorrelation function of MAQ process is equal to rho k equal to gamma k upon gamma 0. Then in the numerator we substitute the value of gamma k from here, this value of gamma k, and in the denominator we substitute the value of gamma 0, which is equal to 1 plus theta 1 square plus theta 2 square, so on plus theta q square, and this finally gives you the autocorrelation function. Autocorrelation function of MAQ process is non-zero for k equal to 1, 2, so on up to q, and it becomes 0 for k greater than or equal to q plus 1. So, the autocorrelation function of MAQ process vanishes for k greater than or equal to q plus 1. Now, this is a special characteristic of autocorrelation function of MAQ process, and this characteristic helps you in identifying the order of the moving average process. Suppose you have an observed time series and you obtain the sample autocorrelation function of the time series and you plot it. And suppose the first 3 autocorrelations are significant, and remaining autocorrelations are insignificant. Then you can say that your time series is from a moving average process of order 3. So, this is how the autocorrelation helps you in identifying the order of the moving average process. You can also obtain the autocorrelation function using the autocovariance generating function. For example, if you consider the MA1 process, so y t is equal to theta b u t and theta b is equal to 1 plus theta 1 b. Then you can easily obtain the autocovariance generating function, and we use the result that gamma b is equal to theta b theta b inverse, which is equal to 1 plus theta 1 b 1 plus theta 1 b inverse. Again you can write it as theta 1 b inverse. Of course, we take sigma square u also here, plus 1 plus theta 1 square b to the power 0 plus theta 1 b sigma square u. Now, this term gives you gamma 0, means gamma 0 is equal to sigma square u 1 plus theta 1 square, and gamma 1 is equal to sigma square u theta 1, and all other gamma k's are equal to 0. Similarly, you can obtain the autocorrelation function of the MA2 process also by using the autocovariance generating function. Again, gamma b is equal to theta b inverse, which is 1 plus theta 1 b plus theta 2 b square 1 plus theta 1 b inverse plus theta 2 b minus 2, and then we multiply these two terms and collect different powers of b. So, you get theta 2 b inverse. Of course, you also take sigma square u here. So, this is equal to sigma square u times plus theta 1 plus theta 1 theta 2 b, sorry, here you have b minus 2 b inverse plus 1 plus theta 1 square plus theta 2 square b to the power 0. Then you have this term theta 1 plus theta 1 theta 2 b plus theta 2 b square. So, from here you can easily obtain gamma 0 equal to this 1 plus theta 1 square plus theta 2 square sigma square u, gamma 1 is theta 1 plus theta 2 sigma square u, and gamma 2 is equal to theta 2 sigma square u. And then gamma k is equal to 0 for all k greater than or equal to 3. So, you can easily obtain the auto covariances and then the autocorrelations also by using the autocovariance generating function. Now, here I have plotted the ACF of MA2 process. So, this is the process. So, if you calculate the ACF, then rho 1 is equal to theta 1, which is 0.6, 1 plus theta 2, 1 plus 0.2 upon 1 plus theta 1 square plus theta 2 square. Then finally, you obtain 0.5143, and similarly rho 2 is equal to theta 2 upon 1 plus theta 1 square plus theta 2 square, and rho k is equal to 0 for all k greater than or equal to 3. So, rho 0 is equal to 1, and then you get rho 1 here 0.51, and then you obtain rho 2 here 0.14. All other autocorrelations are equal to 0. Now, we discuss random walk model. Random walk model is not a stationary process. Suppose ut is a purely random process and it has mean 0 and variance sigma square u. Then a random walk process yt is defined as yt equal to mu plus yt minus 1 plus ut. So, yt depends upon just previous observation yt minus 1, and yt minus 1 has weight 1. So, this model or this process is called the random walk process. Suppose you start with y naught equal to 0, means your initial observation y naught is 0. Then y 1 is equal to mu plus u 1. Y 2 is equal to mu plus y 1 plus u 2. Then we write y 1 equal to mu plus u 1. So, you obtain 2 times mu plus u 1 plus u 2. Again y 3 is equal to mu plus y 2 plus u 3. Then if we substitute y 2 equal to 2 mu plus u 1 plus u 2, then you obtain 3 mu plus u 1 plus u 2 plus u 3. And we proceed like this. Then at the tth step, you obtain yt equal to t times mu plus summation I equal to 1 to t ut. Now, if you look at this equation, and you focus on this term t times mu, then it looks like that y t has a linear trend. Of course, the original model does not have any linear trend, but after recursive substitution, when you come to this equation, it appears that the process has a linear trend. In fact, this trend is called the stochastic trend, and if you obtain the mean of the process, means y t is equal to t times mu plus summation j equal to 1 to t u g. So, expectation of y t is equal to t mu. So, the mean function expectation of y t depends upon t. Similarly, if you obtain the variance of y t, then this is equal to summation expectation of summation j equal to 1 to t u j whole square, and then you take product the square of this term, and only these terms have non-zero expectation, all cross product terms have 0 expectation, and expectation of each of these terms is sigma square u. So, what you obtain? You obtain t times sigma square u. So, you observe that the variance of y t also depends upon t. So, since the mean and variance of y t depend on t, the process is neither mean stationary nor variance stationary. It is a non-stationary process. One more thing you observe that as t increases, the mean of the process keeps on increasing. Not only that, the variance of the process also keeps on increasing. Means, what is variance of the process? It is t times sigma square u. So, the variance of the process also increases as t increases. Means, as t increases, there is a lot of variability, there are lots of fluctuations which you observe with random walk model. Now, this is a very special phenomena, means variance keeps on increasing. In some sense, you can say the process explodes, its fluctuations keep on increasing. There are many time series which behave like a random walk. In practice, you obtain many economic time series. Some of the examples are share prices, real exchange rate, GDP, etc. So, these time series behave like a random walk, and it is very important to identify whether your time series is a random walk or not, because if it is a random walk, then it will behave entirely differently. Here I have plotted two data sets from the random walk model. For first simulated data, we have taken 1000 observations, and here mu is equal to 0. So, for mu equal to 0, you observe that this term vanishes. So, there is no trend. But if you have mu equal to 0.1, then what happens? You have very small value of mu, but still it seems that the process has some trend. Further, as time increases, there are a lot of fluctuations also. Of course, we will discuss this topic later on along with other non-stationary processes, but it is very important to identify whether your process is a stationary process or it is a random walk. Just for example, suppose you have two time series and you are running a regression. Then for running a regression between two time series yt and xt, what assumptions you require? You require the assumption that both xt and yt have finite moments. But here the moments of the process means if xt and yt are random walk, then as t increases, the variance of the process keeps on increasing. And if it is a long time series, then you can say that variance means it is not finite. If the time series is very long, then you may have problem in running regression between yt and xt. That is why the assumption of stationarity is very important, because once you relax this assumption, once your process is non-stationary, then you will face several problems in applying your classical inference procedures like your regression technique. So, today in this lecture, I have discussed the moving average process, and in brief I also discussed random walk model. In moving average process, your time series yt is generated by the past shocks. Its value depends upon the past shocks, and plus of course the current shock also, and it is not directly affected by the past observations. So, you can say that it has memory of past shocks or the shocks connected with the past observations, but it does not have memory of the past observations. In the next lecture, I will consider another process which is a autoregressive process. Autoregressive process also helps you in modeling several time series. So, here I am going to stop. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that is the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life, you are looking at things from a physical point of view. You are looking at the corresponding changes inside the body, you are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.